Okay, hello everybody. I'm Richard Southwell, and I'd like to talk about the Convergence Dynamics of Graphical Congestion Games. And so, this is a project I did quite recently, and it's joint work with Jianwei Huang, and me and Jianwei Huang are both in the NCEL lab at the Chinese University of Hong Kong. And we also worked with Yanjiao Chen and Huayan Zhang, who are in the Hong Kong University of Science and Technology. Actually, maybe that's pronounced Cheyenne. Oh, I'm not very good at pronouncing Chinese names. But there we go. So the idea behind these systems is they're all about graphical congestion games. So let me start by giving you an idea about what graphical congestion games are. Basically, the idea is that we have some kind of graph structure, some simple undirected graph, and we think of the vertices as players. And the idea is that those players are engaged in a game where they have to select resources to use, and their objective is to get as high a payoff as possible. But being a congestion game, if nearby users are accessing the same resource, then they're going to cause congestion to each other and diminish one another's payoffs. So let's define the congestion level of a player to be the number of neighbours that they have who are using the same resource as them. So here we've got a scenario. These players are using the red and the blue resource, and this guy here has a congestion level of 2. Why? Because they just have 2 neighbours who are using the same resource as them. The idea behind these systems is that the payoff that a player gets is given by some non-increasing function of their congestion level. We keep things very general. And so here's an example, a very simple example. Let's suppose that the payoff that a player gets is just equal to minus their congestion level. That's a negative x is a non-increasing function of x, right? So this is okay. So now we can just work out the payoffs that these different players get in this particular strategy profile here. And these are the different payoffs. So this guy here gets a payoff of -2 because their congestion level is 2, because they have 2 neighbours who are using the same resource as them. This guy here is quite happy, and they're getting a payoff of 0 because they don't have any neighbours who are using the same resource as them. Now, the idea behind our systems is we're going to suppose that they evolve. You see, the title of this project is the Convergence Dynamics of Graphical Congestion Games. So the kind of dynamics which we're going to be thinking about are things like better response updating. In better response updating, we assume that the system evolves through time because the players asynchronously change their choices of resources. And also, note that these systems are so-called singleton graphical congestion games. What does the word singleton here mean? It means that these players are only using one strategy at one resource at any given time. Later we'll consider generalizations of that idea, but for now we're just assuming that these players can use single strategies at a given time. Okay, so the idea, as I say, is that we suppose the system evolves because the players within do asynchronous better response updating. So if we assume, for example, that this player updates, which might well be the case, since they're getting quite a low payoff because they're suffering quite a lot of congestion, then if we gave this player the option to update, they would decide to change to the blue strategy, the blue resource. And this would be the resulting state, which is, in fact, a pure Nash equilibrium. A pure Nash equilibrium is a state from which no player has an incentive to deviate. Okay, so I'll give you a more kind of formal definition, really. These are the ingredients that go into a singleton graphical congestion game. We need a graph, obviously. Here's an example with 3 vertices. The different vertices represent players. We need some resources. We use colours to represent resources, like here we have red, blue and green. And now this is the intricate bit. We have payoff functions, but we keep things very general. So we allow payoff functions to be player dependent and resource dependent. And so the only restriction that we make is that the payoff function should be non-increasing, because that fits in with the character of the congestion game, i.e. players want to avoid congestion. But the point is that different players can have different payoff functions associated with any given resource. So, different players can have different tastes of the same resource, and also different resources can have different payoff functions associated with them. So here would be an example. And note how we have a payoff function defined for each player and each resource. Now a state, otherwise known as a strategy profile, that's a scenario where every player chooses one resource. And this is the basic flavor of the game. Every player picks a resource, and then the players get payoffs. And the payoff that a player P gets for using a resource R, is just given by the appropriate payoff function, FPR, of the congestion level of that player. So the payoff that they get depends on who they are, which resource they're using, and how congested that resource is, i.e. how many neighbours they have who are using that same resource. So here's an example. This is an example of a state here where we have player 1 and player 2 using the green resource and player 3 using the red resource. So let's compute the different payoffs that these different players get in this particular state. Well, in this particular state, player 1 here is using the green resource, so they're going to get a payoff of F1 of green of their congestion level. Their congestion level is 1. Because we just have one neighbour using the same strategy. And F1 of green is the function 9 minus 2x. So this guy gets a payoff of 9 minus 2 within this particular strategy profile. And if you want, you can pause this video and check that the other payoffs are as specified. Okay, and so these singleton graphical congestion games have been studied before. Particularly by Kem-Tekin et al. Kem-Tekin, Min-Yang Liao, myself, and Jianwei Huang, we wrote a paper about this and about how these systems can be applied to games on graphs. And we proved various results about these singleton graphical congestion games. In particular, one of the important results is that when the resources are homogeneous, in other words, when the payoff function is not dependent on the resource, when all the resources look the same, essentially, these kind of systems always have pure Nash equilibria. And even better, the systems can always reach these Nash equilibria in polynomial time if you just let the systems evolve via those asynchronous better response updates. So these systems with homogeneous resources have some nice properties. So that's the good news. The bad news is that if you look at the more kind of general cases, where your payoff functions are player dependent and resource dependent, you no longer necessarily have this property that the system can self-organize. Worse than that, there might not even be any pure Nash equilibria. You can find examples of systems with heterogeneous players and heterogeneous resources which don't even have pure Nash equilibria. Okay, so now I want to talk about a few scenarios which can be modelled by these kind of graphical congestion games. One example would be where the players represent different shop owners and the resources represent different kinds of customers that these shop owners might wish to target, or equivalently different kinds of products. And you can see hopefully why this kind of thing would correspond to a graphical congestion game. If two nearby shops both decide to sell suits, then they're going to lose out because they're both targeting the same resource. They're both targeting the same class of customers, and they're going to lose sales to one another. So that's essentially a congestion effect. So if everyone around you is selling suits, you might be better off selling women's handbags or something like that. Another example is in biology. So different organisms eat different kinds of things, and if an organism has the same food source as many of its neighbours in space, then it might suffer food shortages. And so one can imagine that over time organisms evolve so that there's a kind of diversity, and an organism won't be eating the same thing as all the other organisms around them. And a third example, which is a little bit more concrete, is wireless networks. So wireless networks need to use channels in order to communicate, and wireless devices need to use channels in order to communicate. But the thing is that if nearby wireless devices are using the same channel, then they generate interference to one another. And so wireless devices which are close to each other in space will want to use different channels to one another in order to decrease interference and increase the quality of service that those wireless devices provide. So there are these three fairly important real-world motivations for studying graphical congestion games. But I think that in each of these three scenarios, one can make a case that a kind of generalization of the singleton graphical congestion game is called for. Because in each of these cases, our individuals can really use multiple resources simultaneously. I mean, shops can sell many different commodities at the same time. Organisms can eat many different types of food at the same time. And many modern wireless technologies can access multiple channels simultaneously. And so these reasons kind of motivate us to study a more general kind of system, a graphical congestion game where players can access multiple resources simultaneously. This kind of idea. So now our strategies are sets of resources. Before the strategies of our players were just resources, but now our players are deciding which set of resources they should use at a given time. For example, in this scenario here, this user is using resources red, blue and green all at the same time. And we can generalize our notion of payoff in a fairly natural way by saying that now the payoff of a player is just the sum of the payoffs that they get from using their individual resources over all the resources R which they're using. Okay, so this guy gets, say this is player P, this guy gets a payoff of FP of red of whatever the congestion level of 1, because the red resource has a congestion level of 1, plus FP of green of 0, because they have 0 neighbours using the green resource, plus FP of blue of 0. Okay, so we can generalise the systems quite naturally in this way. So here are a couple of payoffs for players in the system. Okay, so I call this kind of thing a extended graphical congestion game. The basic idea is that we have a graph and we have resources, and we have a non-increasing payoff function for each player and each resource. So these three things are just like what we had before. But we've got an extra thing now because our players are now choosing sets of strategies to use. And so every player makes a choice during the middle of this game. So what's the collection of all different choices that they have? Well, that's actually a set of sets, if you like. So the collection of all sets of resources forms the strategy that player P can use, forms the strategy set of player P. And so we can really make these systems very general. We can suppose that there's a certain load of sets of strategies, and player P is limited, and they have to pick one of those sets. So S of P is a set of sets, or if you like, a collection of sets of resources, and player P has to pick one of the sets within this collection to use at any given time. So here's an example. Like player 1 here, they only have 3 options. They can choose to use the red resource, they can use the red and the green resource at the same time, or they can use the red, the blue and the green resource. But they are player 1's only options, and they have to choose one of those 3 eventualities in this system. Okay? So now we've really made our systems very, very general, and we can define the strategy sets of the players in different ways and investigate what kinds of effects that has on the game. Okay, so what about the simplest possible case? Well, in the simplest case, we can just allow our players to use any subset of the resources which they like. And so the set of all subsets of something is called a power set. So I call this power set graphical congestion game, because each player can select any subset of the resources to use. And so a good question then is, do these kind of power set graphical congestion games always have pure Nash equilibria? And the answer is that yes, indeed they do. This is good news and quite surprising really, because these are very general systems. They have, heterogeneous resources potentially, heterogeneous players perhaps, and, really quite complicated strategy spaces. But they always have pure Nash equilibria. Okay, so how do we actually reach the pure Nash equilibria? How about better response updating? Does that always lead to a pure Nash equilibrium? The answer, unfortunately, is no. So here's an example of a game which has 3 players and 4 homogeneous resources. And in this system, the better response updating is not guaranteed to get you to a pure Nash equilibrium, because there's this example here where you can just keep doing better response updates and you can get back to the state that you started from. Better response updating is not a reliable way to reach pure Nash equilibria. Okay then, so what do we do? Well, we know that a better response is not a strong enough concept. So what about the idea of a best response? A best response is a special kind of better response update which maximizes the payoff that a player gets. I'm not sure if better response updating is good enough to always get you to a pure Nash equilibria, but I am sure that this special kind of best response updating that I call a lazy best response update, lazy best response updates will always drive any system into a pure Nash equilibrium. So this is one of our main results. So I should define for you what a lazy best response is. Basically, when you do a best response update in one of these systems, what you're doing is you are changing the set of resources you are using, and you're essentially starting to use a set of resources which maximizes your payoff given what your neighbors are doing. And so if there's only one possible set of resources which maximizes your payoff, if there's a unique best response, then that best response is automatically lazy, okay? But there might be some cases where there might be multiple resources which are tied as best responses. And in those kind of cases, we have this kind of lazy best response idea, which gives us something like a tiebreaker. So we can use this idea to select one of the best response updates. And the idea is this: we'll call a best response update lazy when it's a best response update and when it minimizes the number of new resources that you're starting to use, plus the number of old resources which you're stopping using during the transition from what you're currently using to this thing that you're going to start using when you do the best response updates. So in other words, it's kind of a best response which minimizes the amount of work that you have to do. So it's an important idea, really. It forms the keystone of this research, And usually you don't need to go into these details because usually there'll only be one best response available, and that will automatically be a lazy best response. But in rare cases, there'll be multiple best responses, and then if you're intent on doing lazy best response updates, you're going to pick the one which involves the least amount of work, which involves changing your strategy set or your resource set as little as possible. Okay, so why is the lazy best response idea so important? Well, the reason is that, as I've already said, better response updating won't necessarily get you to a pure Nash equilibrium, but what's remarkable is that lazy best response updating is actually guaranteed to drive the system into a pure Nash equilibrium. So if the players are doing asynchronous lazy best response updates, then whatever the system is, say it's got n players and r resources, then whatever the system is, whatever state it's in, and whatever graph structure you have, the system's guaranteed to go to a pure Nash equilibrium within r times 3 n squared minus n lazy best response updates. So this is really important because this is a massive collection of different systems, and they all have this really nice convergence property. It means that the pure Nash equilibria can be found in polynomial time, and the players can organize themselves into these Nash equilibria very easily, because I think in reality rational players would wish to do these kind of lazy best response updates because they maximize their payoff and they minimize the amount of work you have to do to achieve that. So it really makes sense. Okay, so that was a little bit about these power set games, and I think these power set games could be applied to some scenarios. But there's also another idea, another special kind of these extended graphical congestion games, which I think is particularly appropriate for modeling some of these different scenarios. You see, yes, shops can sell multiple products, and yes, animals can eat multiple food sources, and yes, wireless devices can access multiple channels. But in each of these cases, the individuals have a certain attention bound. I mean, a shop cannot sell millions of commodities at the same time, and a frog can only eat a limited number of different food sources. Wireless devices have limited power, and so they can only access a limited number of channels at the same time. And so I think a fairly important kind of system to consider is the kind of graphical congestion game which I call a bounded attention graphical congestion game. So this is a special kind of extended graphical congestion game where the players can use any set of resources that they like with one restriction, and that restriction is that they have what I call an attention bound, KP, and that means that they can't use more than KP resources at the same time. This is kind of like a cap on how much player P can multitask. So for example here, player 1 has his K value set equal to 3, so they can use any subset of the resources with 3 or less elements. This guy has slightly lower attention level, and they have a cap of 2 here. So player 3 here, which has K3 equal to 2, they have a strategy set equal to the set of all subsets of the resources which have 2 or less elements. Okay, so these bounded attention graphical congestion games, these are really a more general idea than the power set graphical congestion games. And I think it's a fairly important thing to ask what kinds of properties do these systems have? Do they always have pure Nash equilibria? Do they have nice convergence properties? Well, in fact, in the general case, these systems don't always have pure Nash equilibria, because the example I was talking about before, with respect to the singleton graphical congestion games, actually basically corresponds to an example of a bounded attention graphical congestion game with no pure Nash equilibria. So these systems are not, in general, forced to even have pure Nash equilibria. But in the special case where the resources are homogeneous, these systems do have this same kind of nice convergence property that we saw before, that the system will converge in polynomial time to a pure Nash equilibrium under lazy best response updates. In fact, I was able to prove a much more general result than this using a very similar proof technique. By the way, these convergence proofs are based on using potential functions which have integer values. So if you can bound them above and below, you can show that the potential function always goes up in steps, then you can show that the thing can't run forever, so it must stop at a pure Nash equilibrium. Anyway, there's a much more general version of this theorem, which is this one here, which says that any graphical congestion game with n players and R resources, which are homogeneous, and which has this property that the strategy set of each player forms a matroid. I'll talk about that in a second. If we have all these features, then the system's guaranteed to converge to pure Nash equilibria from any initial condition within this polynomial amount of time here, when we evolve the thing under lazy best response updates. So basically what this theorem's saying is that when our strategy sets have a special form, in other words, when the collections of sets of resources that the players have available to them have special forms, then the system has this nice convergence properties. And we also require homogeneous resources here. So what does this word matroid mean here? Well, a matroid, given some sets, a matroid is a collection of subsets of that set with the following properties: that the empty set belongs to the collection if B is a member of this collection and A is a subset of B, then A also belongs to the collection. And if A and B belong to this collection and A has more elements than B, then there's going to be an element H of A which is not in B, and such that if we do add this element to B, so if we get B union H, then that's also an element in X. So matroids, they take a while to get used to if you haven't seen them before, but they're very important combinatorial objects. And this theorem here is really a special case of this theorem here, because in this theorem here, the collections of available resource sets of the players, each of them has the form that it's just equal to the set of all subsets holding less than or equal to a certain number of elements. And a collection of subsets like that is a matroid. So this theorem here is really a special case of this theorem here. Okay, so that's pretty much the end of my talk. I'll leave you with this kind of Venn diagram, which illustrates the different pieces of the space of graphical congestion games which we've explored. And these are a few results which we've found out. There's many different kinds of graphical congestion games, and it's a really interesting and ongoing project to try and classify what features they have. I'm Richard Southwell. Thank you very, very much for your attention, and have a nice day.